Get ready to enter a brave new world with your host, Vasant Dhar.
What is the nature of intelligence? How does it arise? How do humans manage to learn so much so easily? Not surprisingly, the human brain offers some insights into what's really going on in our heads. I mean, we've looked inside and found the brain to be an incredibly densely connected bunch of things called neurons that let us accomplish so much. Somehow, based on this gelatinous goop, we're able to learn how to recognize the world around us, to reason about things, feel emotion, make decisions, and make some incredibly creative inductive leaps. My guest today is Yann LeCun, who is a pioneer in artificial intelligence. His work is motivated by how the human brain works. It has led to major breakthroughs in vision, where machines are now able to learn how to see the world, and I mean see literally. Driverless cars would not be possible today without a technology called convolutional neural networks, with which Yann is associated. Yann is the winner of the Turing Award, which is like the Nobel Prize in computer science. He's a colleague and the founding director of the Center for Data Science at NYU, which is now thriving, and where I co-direct the PhD program. Yann is also chief scientist at Facebook, so he's a pracademic, applying AI to real-world problems at scale, such as content filtering. Indeed, Facebook wouldn't be able to function these days without AI. I'm looking forward to this conversation with him. Yann, welcome to Brave New World. I'm delighted to have you on the show.
Real pleasure to be here.
So Yann, let's start with, where we are and where we're going in this brave new world of AI. So, 30 years ago, if someone had told me that cars would be driving themselves in my lifetime, I would have assumed that they were smoking something. In fact, if they'd told me that you could ask a machine a question in English and expect an intelligent answer, my response would have been, yeah, right. And here we are. And, you've been instrumental in helping the field of AI get here. So tell us about this journey and, what's led to your spectacular success, and how has the success been intertwined with the history of AI?
Well, that's a very long story you're asking me about. I'm not sure you want to hear the entire story, but
I got time.
Okay. I've always been interested since I was a kid, and probably, even more when I was a college student, in sort of the mystery of intelligence, if you want. Like, where does intelligence come from? How does it emerge from the brain in, animals and humans? How did it evolve? Things like this. And so that was sort of the big scientific question for me, besides a bunch of others. And so I got interested in this, and because I was studying electrical engineering, I got interested in, can we build machines that, perhaps would work a little bit like the brain or something like this. So I started getting interested in neuroscience and did a couple projects with a few professors at my engineering school and started, digging the literature. And the reason I got embroiled in this is because I stumbled on a book that was a debate between Noam Chomsky, the famous linguist, and Jean Piaget, the developmental psychologist. And they were arguing the nature-nurture debate, like is language learned or innate? And among the people kind of in that debate was MIT professor by the name of Seymour Papert, and he was talking about a model called the Perceptron. So I read this around 1980, 1981. I was still an undergrad, and the Perceptron is one of the early learning machines, if you want, that people had come up with in the 50s. And so I learned about the fact that you could actually build machines that could learn. And I found that really fascinating. Maybe because I'm lazy or not smart enough, I always thought that it would be very difficult for human engineers to design intelligent machines from scratch. And so I thought, learning was probably kind of a good idea to go about that. So I dig the literature and realized that there was basically no literature at all on the topic after, the late 60s, early 70s. People had basically abandoned this idea of, trying to, get inspiration from the brain to build intelligent machines. So AI in the early 80s was symbolic AI, was expert systems. And here I was kind of trying to dig information about what we now call neural nets or deep learning. And there was basically no one working on this at all. So that's how I got started. And, things happened after that.
So why had the field abandoned neural nets. And I say this, by the way, because, I went to Wall Street, took a few years off from academia in the 90s, and people would say, you're not using neural nets, are you? And they'd roll their eyes. And
Right.
I'd say, no, not at all, And this was like a carryover from, I guess, from the time you're talking about. So why had the field abandoned neural nets, which, on the surface seemed like, hey, we've looked inside the brain and it looks like a neural net. So why had they abandoned it?
Yeah, the field actually abandoned neural nets twice. And so we are in the middle of the third wave, if you want, of neural nets. So the first wave was, started with the cybernetics in the 1940s and 50s, the perceptron in the late 50s, and then there was a bunch of work. And the work ended in the late 60s because of, several things, because of limitations of the models at the time. They were capable of learning, but their capabilities were very limited. And there was a book that was published that showed that those limitations basically were so great that, there was no way by pushing this kind of technique, we're going to be able to build intelligent machines. Might be able to build, adaptive filters or pattern recognizer or simple things, but not intelligent machines. It turns out that book was written by Seymour Papert, the same one who 10 years later was singing the praise of the perceptron on behalf of Jean Piaget, and a very famous person in AI called Marvin Minsky, who started when he was a PhD student building neural nets through electronics and then kind of abandoned the whole idea and was sort of a big advocate of sort of logic-based AI. So neural nets sort of, fell out of favor in the late 60s, early 70s, except for a few people, mostly in Japan, who kept working on it because Japan had its own research ecosystem that was kind of not subject to the same fashions as in the West, if you want. And then there was a revival in the mid-'80s due to a number of different factors, but mostly due to the interest of physicists in the question of neural net. And the physicists didn't care about the fact that perceptron didn't work. In fact, they didn't know about it. So it kind of made the field kosher again, sort of respectable again, at least for physicists and engineers. And then slowly, computer scientists kind of got interested in this again. And then there was a watershed moment in the mid-'80s where the so-called backpropagation algorithm was invented. So this is a method for training neural nets whose capabilities are considerably, expanded compared to the old models from the 60s. And that opened the door to sort of many more applications. People were really excited about this. So there was a wave of interest in neural nets between roughly 1985 and 1995. And I think by the time you got to Wall Street, that wave already had died. And so again, neural nets were a bad words between after the mid-90s, roughly, until, the early 2010s.
It's interesting, you referred to, symbolic AI and logic. I remember this conference I was in California, and I forget when it was in the 90s, and Lotfi Zadeh was the keynote speaker. And I remember, he got up there and said, the problem with AI is that it sort of hitched itself to the wrong post, and he said logic is just not the right way to look at intelligence. And in fact, fuzzy logic is the right way to look at intelligence, right? And he'd got the Honda Award in Japan, and and they were like really big into sort of fuzzy logic in Japan. But I guess you would argue that this time around, AI has indeed hitched itself to the right post, wouldn't you?
Well, I mean, there are kind of two posts, and one of them is sort of the classical computer science approach, right? You do logic, you do search, you do sort of combinatorial exploration, you do pathfinding, things like this. The stuff you find in, what's called good old-fashioned AI textbooks, right?
Yeah.
And there's a lot of value to this. A lot of algorithms came out of this. There's a lot of things that we use, every day that came out of that kind of research. Like you plan a path on your GPS or your Google Map or whatever, and that's using path planning algorithms that were designed in the context of this sort of more classical approaches to AI. But then there is another one which is chaining yourself to the sort of inspiration from biology and learning, really. And that's what, deep learning, neural nets, and machine learning more generally really is attached to. Both of those approaches have advantages and disadvantages. Right now, everybody is excited about the learning-based methods because there's a lot you can do with it that the other set of methods cannot do, and vice versa, unfortunately. So we haven't found, a set of techniques that can do everything. So what's easy to do with the sort of machine learning-based methods deep learning in particular, sort of modern forms of neural nets, is perception and things that don't require kind of reasoning, if you want. So things an animal or humans could do very quickly without thinking about it, basically, that is sort of at the level of subconscious, right? And then the type of stuff you can do with sort of logic-based AI is the kind of stuff you can verbalize, the kind of stuff you can explain. You can reduce it to a set of rules and facts. And those two are right now incompatible with each other. So we don't know how to make reasoning systems that are compatible with machine learning. That's one of the issues that needs to be addressed.
So you'd say that that's sort of probably one of the biggest challenges in AI, right? Because we have these sort of plurality of methods. They're all good at something. They have their strengths. And at the moment, machine learning, and in particular deep learning, is big because, it's working and it's working really well. But at some point, we'll have to come back to this sort of synthesis that we'll need to make, because, you start off by saying, the intelligence is a really elusive concept. It has sort of multiple dimensions to it. And, in the age of symbolic AI, we sort of thought we knew, what made us intelligent. And, that doesn't seem to be the case. So I guess what I hear you saying is that the big challenge right now is sort of the integration of these methods towards systems that can learn and reason sort of in a more facile and fluid way.
Well, it may or may not be an integration. That's the problem, right? I mean, there are advocates of integration, essentially. But, some people call this neurosymbolic or something like that. So basically getting neural nets to manipulate symbols. And then there is sort of different degrees of, how you kind of hardwire the symbol manipulation machinery in neural nets. So that's one possible approach. Another possible approach is that if you look at the animal world, very, very few animals and probably very few humans are actually capable of long chains of reasoning and logic, if you want. A lot of the knowledge in animals, and most knowledge, I think, in humans as well, has nothing to do with logic and reasoning. It has to do with understanding how the world works and, being able to simulate the world, to basically, predict the consequences of your actions and things like this, right? So that's the form of intelligence that you find in humans and animals. And then logic, it's only a few humans in the last 3,000 years that basically have been able to do it. So in a way, logic is kind of a small epiphenomenon of intelligence. The bulk of intelligence is somewhere else. Understanding how the world works, building models of the world, and how to learn this, I think, is the big challenge that we've faced.
Right. So I guess you mentioned earlier that, or at least I read you saying this, that the major progress, I guess, the push has been that we managed to make a big dent in perception. And before that, we sort of had to somehow fudge that, right? Because machines couldn't see, they couldn't read. And so you had to do so much work to get problems into sort of a representation that the machine could sort of deal with. Whereas perception just kind of knocked down that barrier and said, okay, now, the machine can sort of talk directly to the world or see the world directly.
Right. The classical way of building a pattern recognition system until fairly recently, so before the sort of, advent of deep learning, if you want, was to basically build a system in two parts. If a first part would be heavily engineered, and it would be the part that takes the raw signal, whether it's an image or an audio signal, speech or whatever, and then turn it into a form that essentially detects the salient features in the input. So for speech, it would be, is there energy in this frequency band at that time or not? And by having the list of levels of energy in various frequency bands, you can sort of more or less, by matching this with a template, you can tell what sound is being pronounced more or less at that time. For image recognition, like for recognizing characters, like doing optical character recognition, it's the same thing. You would, extract some features. Are there corners? Are there loops? Are there things like this, right? So you would have kind of a list of features that indicate the presence or absence of each of those features, and then you would feed this to what's called a classifier. And a classifier at the time, many of them were very similar to this perceptron from the 50s and 60s. So that, that was the classical way of building a pattern recognition system, or a machine learning system for that matter. And what deep learning changed is, in deep learning, you don't have to build this sort of handcrafted, hardwired feature extractor. You build your neural net as kind of a cascade of multiple layers of trainable, adaptable modules, if you want. And the system learns end to end. So it learns to figure out what are the salient features, how to combine them to detect motifs, and how to combine those to detect parts of objects, how to combine those to detect objects. And so you have this sort of, hierarchy of abstract representations that is automatically learned by the, one of the downsides of this is that you need two things. You need a lot of data, and you need powerful computers, and those only became available fairly recently, essentially.
Right. I mean, it's actually pretty amazing when I look at the sort of progress that we've seen in vision and language, that, how it's just taken off. And, one of the things I'm struck by is the complexity of these models, right? I mean, it almost looks like, because of all the data that we have, that, complexity has like sort of paid off big time, with these models that have like gazillions of parameters. And by gazillions, I'm talking about, 10 to the 15 or 18, just like really large numbers. And the tools are amazing. If you want to build these NLP systems now, you can grab these ready-made tools, without a clue about the underlying complexity and the assumptions.
That's right.
And, I just sort of wonder whether this will, is this something we should be worried about? Is this going to get us into trouble? Like, when should we trust these kinds of models, and when should we be wary of them?
Oh, well, there's a lot of questions there. So first of all, there was a tradition that you read in every statistics textbook, which is that if you have a model with parameters and you need to identify those parameters from data, like you're doing regression, for example, right? You're an economist or you do finance or whatever. You need to have more data than you have parameters. You'll read this in every textbook. And what the second wave of neural nets in the 1980s and 90s showed empirically is that it's not actually the case. You can have neural nets that are fairly large. By today's standard, they're tiny, but at the time they were pretty large. And you train them on relatively small amounts of data, and they work very well. And so they break, one of the main theoretical results, if you want, of statistics. So a lot of theoreticians were extremely suspicious of those methods for that reason. Why is it that those things work, even though they are way over-parameterized? And the kind of neural nets that, we were playing with in the late 80s, early 90s, at most had something like, 50,000 or 100,000 parameters. So they were like, I would talk to a statistician, very famous statistician from UC Berkeley, Leo Breiman. And, he was one of the first statisticians who kind of became really interested in neural nets and tried to kind of figure out what the story was. And every time I would see him, he would tell me, like, I can't believe how big your models are. Like, I just can't believe it. Our models in statistics have 10 parameters and yours has 40,000 or 100,000. Like, what's going on? We still haven't quite figured out what's going on. So, by the mid-90s, as I said, interest in neural nets kind of died. And one reason, so there were three reasons, I think. One reason was that there were very few data sets that were available in large enough quantities that you could use those neural nets advantageously. This was before the internet, right? So the society was not digitized and everything. So there were only a few applications like speech recognition and handwriting recognition, perhaps, where there was enough data. For everything else, neural nets were just too big. There was just not enough data to train them. The second thing is that you needed to write a lot of software to get those things to work. And one of the things that perhaps I and my collaborators at Bell Labs were pretty diligent about doing was kind of writing tools that basically gave us superpowers. So we wrote a tool with my friend Léon Bottou and a few others called SN, which was eventually open source under the name Lush. And it was essentially what we now call a deep learning framework. So it's similar to PyTorch and TensorFlow that we're familiar with today. It was basically the ancestor of all of those things. And it allowed us to play with those models and do all kinds of stuff with them that basically nobody else could do and reproduce our results. And at the time, it was difficult to open source code. So that was the second reason. The third reason is disbelief. So because the performance of neural nets kind of defied, every textbook of statistics, people just did not believe it could work so well. They say, there's something flawed with it, right? So, you have this over-parameterized model, you're training it with, only a few thousand samples and it works well. You're optimizing a non-convex objective function, for those of you who knows what that is. And how can it converge? There is no proof that your thing will converge anywhere. So people basically moved away from it because they could not believe that it was working, despite overwhelming empirical evidence that it was. So I think it was a bit of a disease of the sociology of science, if you want. And it took 15 years to change people's mind. And what we've seen over the last few years is an explosion in the size of those models, right? So the latest, biggest models for natural language understanding have something like 1 trillion parameters in them. Facebook and Google routinely use natural language understanding computer vision models that have hundreds of millions of parameters. So, those things are becoming big, but compared to, any kind of biological brain, they're tiny, actually.
This reminded me of something, and I don't know whether this is widely known about you, that, in like way back when, I guess when you were a relative kid, that your character recognition machinery was used, to process almost 20% of the check volume in the US, and used by the post office to read zip codes and sort mail. What was the complexity of that model? Were you talking like 50,000 parameters? Like, just curious.
Yeah, roughly.
You've come a long way from that time.
It's about that. Yeah, roughly 100,000 parameters, that order of magnitude. Yeah, there's a few videos that you can find on YouTube of, a kind of a 32 years old version of me kind of showing demos of that system. Yeah, so this was built in the early 90s when I was at Bell Labs in New Jersey. And we had, early results in the late 80s on like training what's called convolutional nets. So this is like, a particular type of neural net architecture that people associate my name to, okay, because I kind of popularized them in the late 80s. And, we could train those convolutional nets on characters and do handwriting recognition with a level of accuracy that was really sort of unparalleled at the time. So that was a really kind of a good demonstration of what neural nets could do. But as I said, a few people reproduced this because that required a big investment in software that nobody was willing to do at the time. And so, we built systems around this. We built systems that could not just recognize single characters, but it could recognize a sequence of characters like a check or zip code. We tried to sell it to the post office, but for reading zip codes, and we had prototype systems to do this. But the USPS basically didn't believe that AT&T was going to be sufficiently interested in building this for them, so they didn't go with it. But we sold this to banks. So AT&T had a subsidiary called NCR at the time that was building basically check reading systems for banks, and our system was integrated in NCR machines. As you say, by the end of the 90s, was reading somewhere between 10 and 20% of all the checks in the US. This was probably the big, large-scale commercial success of sort of big neural nets. There were a lot of smaller applications of neural nets all around, but this was, probably the biggest one.
Yeah, tiny, I guess, compared to the kinds of things we're seeing these days, isn't it?
Right.
So, Yann, one of the most elusive aspects of intelligence has been common sense. I remember I spent 6 months down in Austin, Texas in the late 80s at this lab called MCC. There was the Psych project going on, headed by Doug Leonard, dozens of people, trying to get the machine to, quote unquote, understand common sense, just massive effort in that arena. And, most of it, I think it's fair to say, sort of went nowhere. By the end of that, I had no more common sense than they did, before that. Is this an area where you think we are going to make some progress with a new approach? So do we have like a new, with this sort of neural net approach, are we, going to do any better this time around, you think?
The short answer is yes. But there's a lot of qualifiers on that. Okay, so first of all, we don't know how to do it yet. We don't have any techniques today that will allow machines to acquire what we commonly call common sense. And there are some people, I would kind of classify people in sort of 3 different categories. So there is the Doug Leonard type category where, they think common sense is essentially can be expressed in terms of language, first of all, and perhaps in terms of logic. And if you just get enough people to type facts and rules about how the world works in a computer, that machine eventually will have enough facts and rules to be able to infer that, if I have a glass full of water and I turn it by some angle, whatever is underneath will be wet, right? So things like that, right? That have to do with the physical world, but any kind of common sense. So then there is the second category of people who think that still that common sense is linked with language because they think language is kind of a necessary component of intelligence. I don't believe this myself, but there's a lot of people who believe this, which is a very natural thing to do. And they think by training a machine to understand text, by reading a lot of text, a learning machine, a neural net, a very large neural net with tons of parameters, by getting a machine to read everything that has been ever written, that machine will learn enough about the world that some sort of common sense will emerge from it. I don't think this is going to work, personally. I think this is a losing proposition because I think the bulk of our knowledge is not expressible in language. I think the bulk of our knowledge is, as I was saying earlier, how the world works, things like that. And so, sort of the third category where...
So before you get to the third category, just to sort of draw an analogy here. So would an analogy be that, animals don't have the kind of language that we do, but they have common sense?
That's right.
Would that be a reasonable way? Okay.
Yeah, that's a joke I say all the time, which is that, the most intelligent AI systems that we have today have less common sense than your, a house cat. Certainly less than a dog. So, a cat has an incredible amount of common sense in the sense of, being able to, predict a lot of stuff that is happening to themselves or to the world and, being able to act on things and being, incredibly agile and all that stuff. So a cat has a huge amount of background knowledge about the world that none of our machines have. And one big question is, how is it that, cats, dogs, human babies, and a whole bunch of animals can learn so much about how the world works in such a short time? They use a type of learning that we have not been able to reproduce in machines yet. So the way I see the future is that, and this is really what I'm working on and a lot of other people are working on as well, is can we find new paradigms of machine learning, still based on deep learning, but using kind of a new way of using deep learning, if you want, that will allow a machine to learn how the world works essentially by observation, by basically watching videos, maybe also reading text, but there's a lot more information in watching videos. And, figure out that, an object that is not supported falls, right? There is gravity. Figuring out that, an object cannot disappear from one location and suddenly appear in another location. That the fact that if an object is in a certain place and you stop looking at it, or it gets hidden, it's still there, object permanence. So these are very basic concepts about the world that human babies learn in the few months of life. It takes about 9 months for a baby human, typically, to learn about gravity. So if you show a 6-month baby a trick in which an object appears to float in the air, they're not particularly surprised. They're not particularly interested either. But if you show that to a 9 or 10 months baby, they look at it like the entire world is coming to an end because they know that objects are not supposed to float in the air; they're supposed to fall. So around the age of 8-9 months, the babies learn that gravity is a thing. And the question is, how does that happen? What's the principle behind this? They don't learn to do a particular task. Our learning machines are trained to do a particular task, and they can have superhuman intelligence, superhuman performance on this particular task that we train them on. But they are completely helpless if you change the task a little bit. So the question is, how is it that animals and humans learn how the world works by observation without learning a particular task? And then that allows them, any teenager, to learn to drive a car in 15 hours of training. And we still can't do this with our most powerful machines.
That's fascinating. It makes, it sort of conjured up images of like someone growing up in space. And for them, like common sense reasoning would be very different, right? They wouldn't be surprised to see just objects floating around. So in a sense, I guess, what you're saying is that there's this bias in the world around us. I'm using bias in a positive way, like people do in machine learning. And that there's this sort of bias around us towards certain kinds of things. You don't see objects, shooting out of the earth and going to the sky, not unless they're missiles or powered. And so that so I guess that's what you're saying. You just observe, and there's sort of a bias in what you're observing, and that eventually gets reinforced and becomes common sense. Is that sort of a reasonable way to paraphrase?
Yeah, I would say the common sense is the accumulation of those like very basic knowledge about how the world works, how the physical world works, but also how other animate entities act in the world, and everything about the world, basically, which we learn by perhaps training ourselves to predict, essentially, right? So if I show you a piece of a video and I stop the video at some point and then I ask you to predict, to describe to me what's going to happen next in the video, you can have like a few guesses about what might happen. Okay, so it's a video where someone is sitting at a table. There is a glass near the side of the table, and the person hits the glass with the back of their hand, and the glass starts falling. And we stop the video right there. You can tell the glass is going to fall, and the liquid is going to spill, probably fall on the ground. Perhaps the glass will break and everything. There's several possible scenarios. Perhaps the person will catch the glass, in flight or something. But you know how the world works. There's gravity. The different properties of liquids and solids. Certain solids can break when they hit the ground. Things like that, right? If you think about the amount of knowledge you have accumulated about this kind of stuff, it's absolutely staggering. And there's absolutely no way we can get machines to learn this through just, having them read books and written things. There's just too many things in the physical world that have never been expressed in text. So I think that's where common sense is going to come out. When we get machines to learn to predict what's going to happen in the world by, in the rest of a video, for example. I've been actually working on this. The problem is that we don't have good techniques to do this. And the main reason we don't is because we don't have good ways for machines to represent multiple outcomes in a prediction, uncertainty in a prediction, basically.
It's interesting when you were talking about vision and language, I was thinking that, there's a huge amount of data that we get just sort of from observing the world. And you're saying, just by observing, we can learn, common sense, at least visual kinds of common sense or what people call naive physics or something like that you can't get through reading. Which gets me to sort of a related question, and in language, right, where we've made sort of tremendous progress in language through sort of unsupervised learning. And that, by the way, reminds me of the picture about your cake, which I'm going to come back to. But what we're seeing now in language is this concern that, there's just, the bias you have in vision, it's a good thing in the sense that, you're sort of observing the world as it is and learning common sense. But language just seems to be a different animal, right? Where there's, some not so nice kinds of biases in language. And, we're training these machines based on that, and the machines are learning the bias as well. And now people are sort of looking in horror and saying, geez, how do we deal with this? Is there a way of dealing with bias in language, or is that just something we're stuck with and have to be careful about?
Okay, I'll come to this question in just 1 second. I'll start with this. You just mentioned unsupervised learning. I prefer to call that self-supervised learning because really the methods that are used are very similar to supervised learning. So self-supervised learning is this idea that you could train a machine to learn how the world works by, for example, predicting what's going to happen in a video. And what has been very, very successful, so far this has not been successful, but what has been successful is self-supervised learning applied to natural language understanding systems. And the way this works is that you take a piece of text, typically a few hundred or 1,000 word long, and you remove some of the words from that text, and you show that text with missing words to a very large neural net, generally called one of those architectures called transformers. And you train this giant neural net to predict the words that are missing. And by doing so, the neural net has to basically learn a representation of language that contains, the meaning of the word that is missing, the syntactic role of that word in the sentence, right? If I tell you a sentence, the blank chases the blank in the kitchen, there's only a few options for the two blanks, right? It's like, the cat chases the mouse in the kitchen, right? That's just about it, more or less, if we're talking about pets. If I say the blank chases the blank in the African savannah, there's a whole bunch of other possibilities, but you can imagine what they are, right? So you can imagine which word would be appropriate. That it could be a lion and an antelope. It's probably not going to be a lion and a mouse. It's not going to be a cat and an antelope. Because again, you have a lot of common sense. You know how the world works. You know that animals, predators need to be larger than prey or need to be, numerous and stuff like that, right? So there's a lot of background knowledge you can draw on to make that prediction. And by training a system to predict missing words, it learns a bit of that in kind of a shallow way. It learns a little bit of that background knowledge, but it's not enough to really say that a machine has common sense. Okay, so that's the first part of the question. And then you were asking about biases. So machine learning systems that are trained with supervised learning, or even with supervised learning in the case of natural language understanding systems, reproduce, they all reproduce the biases that are in the data. And sometimes, so it looks a bit like a mirror, like some people say that those machine learning systems amplify the biases. I don't believe that's true, but they do reproduce the biases that are in data. And then we look at how they behave, and they behave like the average person on the internet, and we don't like what we see. We see those systems being trained to predict text, right? You give it a little piece of text, and then you ask it to predict the continuation of the text. And the system has been trained on dialogues on Reddit or something like that. And some of those dialogues, there's people who are racist and sexist and all kinds of bad things. And so statistically, the system once in a while is going to say things like that, reflecting the statistics of the text it's been trained on. It's a mirror of humanity, and humanity is not necessarily all nice. I know something about this, working at Facebook.
Yeah, sometimes I wonder how we can expect machines to be quote unquote fair when life is anything but fair. It's almost like we expect something miraculous from machines when we're training them on anything that's
true, and
less than perfect.
And you have to realize that one of the largest deployment of machine learning today, in the entire world, is basically to filter horrible content that people post on social networks, whether it's Facebook, YouTube, Twitter, or everything else. That's a huge application of machine learning. So, people sometimes complain about, social networks being, cesspools of hate speech and objectionable content and things like this. But it would be a lot worse if it were not for AI systems to filter them out. A few of them get through. And it's only in the last few years that, because of the progress in NLP that we just talked about, that companies like Facebook can do a good job at doing it. If you go back just 2 years, I think only about 40% or 30% of hate speech was being filtered out automatically by AI systems back then. And now it's, in the 90s. And that's entirely due to progress in natural language processing. This can be done in just about any language spoken in the world. And so, there's a lot of progress there, and it's making interactions online, a lot better.
So tell us a little bit more, since we're talking about Facebook and research in these big tech companies. What is the vision of AI research at Facebook? Like, what are the big questions? What's the exciting stuff that's happening there and the innovation? What excites you about working there?
So I joined Facebook at the end of 2013, and what I did was create a AI research lab for Facebook called FAIR, Facebook AI Research. FAIR is now part of a bigger organization called Facebook AI, which has roughly 1,000 people. Facebook AI Research within it is about 300 people or so. Facebook AI Research practices open research, so everything is published. Most of the code is open sourced. It's sort of very fundamental, basic open research. A little bit in the style that I was used to at Bell Labs, although there was no open source then. So now Facebook AI, the bigger organization, also has kind of applied research and some sort of technology development groups that basically make AI technology, turn AI technology innovations into kind of useful technology that is deployed in Facebook products. For content filtering, content ranking, translation, image recognition for both filtering and ranking, image recognition for like generating text for the visually impaired and things like that. So, a lot of it for, basically connecting people with each other and connecting people with content and helping people who, otherwise wouldn't be able to see that content or interact with it. So that's a lot of today's application for it. But really the sort of long-term hope of the use of AI within Facebook is things like intelligent virtual assistants, right? So, some of your listeners may have watched the movie Her. It's a Spike Jonze movie from about 10 years old,
mm-hmm.
And it depicts a person who basically interacts with a virtual assistant that happens to be kind of more intelligent than most humans and finds humans a little boring in the end. But the sort of day-to-day depiction of how people will possibly interact with virtual assistants in the future is not a bad one. It's one of the few sort of AI-related movies, if you want, that doesn't get it completely wrong. So, that's one thing that people are after, intelligent virtual assistants. They may live in your smartphone, but they may also live in your augmented reality glasses that you'll wear that will basically, give you, basically augment the world with information. It will do, speech-to-speech simultaneous translation, also visual translation, right? You'd be in a country where you don't even recognize the alphabet, and you look at a sign and your glasses translate it for you, and you see the translated version. So, a lot of things like this that will be coming in the next decades. I'm talking about things for which we don't have the technology yet, okay? But they will be coming in the next decade, and that's a part of the vision. Now, it turns out that was really the vision that got, Mark Zuckerberg and the leadership at, Mike Schroepfer, who is the CTO, and the leadership at Facebook to get into AI. But as it turned out, AI became absolutely crucial to the company for what Facebook called content integrity, which is really filtering out horrible content and things like that, but also doing a good job at ranking. And if you were to take deep learning out of Facebook today, the entire system will completely crumble. I mean, it's completely built around it. You can say the same thing about Google search engine and YouTube and things like this. All of those things are now completely built around deep learning.
Wow, it all sounds like sci-fi, right? Speech to speech, instant, visual translation, all that stuff, right? I started by saying, 30 years ago, would you have imagined this? And it's just like mind-boggling how that genie's out of the bottle now. And, and that these things are actually, seem attainable, like something that would have been just unimaginable just a few decades ago.
But progress in translation has been nothing short of astonishing, really.
Yeah, indeed. I remember when there were these jokes about, the flesh is willing, but the spirit is weak, being translated into, the vodka is great, but the meat is terrible, or something like that. It used to be, that was kind of the level of intelligence we used to expect from machines. Yeah, and it's now like palpable. You're constructing emails and it's like finishing the sentence for you like 4 or 5 words ahead. And you're just like, how the hell did it, do that? And, we become just so blasé about these things. Just expect them now. So, a couple of other things. So do you see, a lot of this progress in the future in AI being driven by these academia industry partnerships, right? I mean, it seems to me that industry's got all the data, and that's sort of, grist for the mill. And so they have the data. And so that's where, a lot of the innovation is going to happen, almost necessarily. I mean, is that what you're seeing? Is that what the future is going to be?
No, not at all. The amount of data that's available to, companies like Facebook, Google, Amazon, and others is good when they are in the process of deploying a machine learning system, for real application in the real world. But for research, to make progress in AI techniques, the data that is used by people in industry as well as by people in academia is public data. Because if you want to do research, right, you come up with a new method and you want to show that your method is better than the previous method, you have to compare yourself on the same data sets that previous people have used. And so necessarily the data sets that are used in research, whether it's academic or industrial research, are public. They have to be public. Otherwise, you cannot really do research. This is an interesting phenomenon, even in industry, that, in a research lab, you have a new idea for a new architecture to do, I don't know, translation, blah, 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 right? You can train and test your system, but until you write a paper and you either publish it or you post it publicly, and people can scrutinize the methodology and then tell whether your numbers actually are kosher on public data sets, your own engineers within the company will not believe you, okay? So having a research lab in industry that actually publishes results helps convincing the product groups within the company that the technology produced by their own research group is actually good. It's a very, very curious.
Yeah, that makes sense. You're pointing to the fact that, it's got to show something on some standard benchmarks. Right. But what about the other side of it, which is, just like the sheer, computational resources required? Do you think that problem is just going to go away? And I was reading someplace that, to train some of these nets requires the equivalent energy of a few transatlantic flights. This is just like serious computation required, is possible at these big shops. I mean, do you think that barrier is going to go down?
Well, okay. I mean, there are several types of research projects you can do. So if you want to build the best, let's say, translation system in the world, and you are an academic group, you're going to have a very hard time because you're going to be competing with, Facebook and Google and a bunch of others that have access to, enormous amounts of computation. They have big groups of engineers. They have, entire groups of engineers working on parallelizing the code so that it runs fast on hundreds of computers at the same time. So you're not going to beat their numbers. There's this very small chance that you're going to beat their numbers. But what you can do is that you can come up with the idea that is going to be the basis for the next translation system. In fact, this story actually happened. So at the end of 2015, there was a paper by Ilya Sutskever, who at the time was at Google Brain. He presented a paper at the NeurIPS conference showing that a neural net-based translation system could basically match the performance of kind of more classical approaches. And his system was incredibly expensive, probably not reproducible by anybody outside Google, except maybe at Facebook or something like that. But it was a bit of a watershed moment because it convinced people that you could do translation with neural nets, and the progress was probably going to be pretty fast. So what happened next was that within a year of this, a group at University of Montreal. So University of Montreal has a very strong AI group called Mila, which was founded and is directed by Yoshua Bengio. And there was a young postdoc there called Kyung-Young Cho, who is now a colleague of ours at NYU, a faculty at NYU, together with an intern called Dmitry Badanov. And they came up with this idea that if you want to build a translation system, you can build a much more compact system than the one that Ilya Sutskever had built by using this idea of attention. So basically, you would have a translation system when it comes to producing a word in the target language. It focuses its attention on the corresponding word in the input sentence. And it's a particular architecture of neural net that can do this. And they showed that, that performance could basically equal that of Ilya Sutskever's. Just a couple of months later, that system was reproduced or perhaps borrowed by Chris Manning's group at Stanford University. And he entered a competition for a translation system and won with that technique. So that was it. Translation now became neural nets, and it was using this attention. And then there was another, big progress when people started using attentions everywhere. So there was a Google paper that said attention is all you need for natural language processing. And, it proposed this transformer architecture that I mentioned earlier, which is sort of a generalization of this idea of attention. And that brought another quantum leap in performance of natural language understanding and translation systems. So what happened once Kyung-Young Cho, Dmitry Badanov, and Yoshua Bengio published a paper, and once Chris Manning had beat the record, the entire industry jumped on this idea, right? Everybody said, this is the way we're going to do translation now. So every lab, Facebook, Google, Amazon, everybody, a bunch of European companies, IBM, everyone started building translation systems on that model. And Yoshua told his lab members, stop working on translation. It's not worth doing anymore because we came up with the idea. Industry picked it up. Now we can't, we're not going to be able to catch up. So, this is a natural evolution of a technology where, it comes out of academia. There is some early demonstration and then, some good demonstration on real data. And then it gets picked up by industry. And then, it's out of the hands of academia. Academia needs to look for the next idea. That's the way it works. That's the way it should work.
So what do you see as the most exciting areas in AI research these days?
I can mention two, and I already mentioned them to some extent. So one of them is this idea of self-supervised learning. How do we get machines to learn how the world works by observation? And when I say the world, it doesn't need to be the physical world. It could be whatever environment that we're interested in the machine understanding. So a little bit like babies observing the world and realizing after 9 months that objects that are not supported fall. So things like that. So that's the idea of self-supervised learning. Right now, it's unbelievably successful in natural language processing. It's starting to have some success in computer vision, object recognition, and things like this. There's been quite a lot of success, very recent success in speech recognition, where self-supervised learning really has improved the performance of speech recognition systems, or at least decreased the amount of data that is required to train a speech recognition system. And that has practical consequences, because what you can do now is that instead of training a system to recognize English, so translate English speech into English text, and then another one for French, and another one for Spanish, another one for Mandarin, another one for Urdu and Tagalog and whatever, what we can do now is basically train a single large neural net to essentially translate any speech in any language. And the advantage of this is that because there's now a single network and there is redundancy between different languages of the same family, you don't need as much data to train a single speech recognition system. You can train a speech recognition system in some new language with a very small amount of data, because that new language is similar to some other language. Maybe it's a dialect of another language that a couple other languages that your system has already learned. So that enables a lot of things. This is very important also for things like hate speech detection. You want to be able to detect hate speech regardless of language. Very important language, for example, to detect hate speech in are languages spoken in countries where there are, religious or ethnic rivalries, for example, because you don't want, one set of people to, cause violence by, spewing hate speech on social networks. So you have to be able to do this in basically every language in the world, and it's very, very hard. But now it's kind of becoming possible. So, that's a little bit where the thing is going. So self-supervised learning, that's the first big area I think that's really exciting. And because I think, not just because it's useful, but also because I think it's going to be the ticket to machine common sense eventually, and the next step in AI, in progress in AI. Then the second thing is what we were talking about earlier, which is getting machines that can simultaneously learn, but also reason. Okay, so a machine whose output will not going to be computed by, running through a few layers of a neural net, but a machine that will basically think about an answer before producing an answer. And, there's a lot of people working on ideas around this, but no real complete satisfactory solution yet. How do we get machines to reason in ways that are compatible with learning? We can get machines to reason using logic, but they can't learn. Or we can get machines to learn to perceive, but they can't reason. And so we need to kind of, push towards machines that can learn and reason.
This is really fascinating. It's sort of, what you're describing almost sounds like, the ability for it to introspect, And I may be going to Twilight Zone, but sort of it reminds me of the first time I read about some of, yours and Rob Fergus's work on, trying to make, neural networks more, interpretable, the sort of deconvolution and sort of make them more visible. And I was wondering, these machines have gotten so complex now, and people say, oh, you've got to make them explainable. And I'm like, what does that even mean, right? To make these massively complex networks explainable, with a gazillion parameters. And I was thinking, well, the only way this is going to happen is that the machine itself is capable of explaining, of looking at itself and saying, okay, here are the patterns I'm seeing in what I've learned, and maybe that becomes a basis for, quote unquote, introspection and explanation. But maybe I'm just out in Twilight Zone. But what you were talking about just made me think of, what it actually even means to reason.
Okay, right. So I have a bit of an unorthodox position on this, which is that I don't believe that in most cases, explainability of, decisions of AI system is particularly useful. The vast majority of AI systems that are in use today and will probably be in use in the future do not require explanation for the decisions they make. A few do, right? And it's the ones that do are the same type of decisions that we require humans to provide explanations for as well. So if you have a judge making a decision about a court case, they have to write an opinion about this case that would be recorded in jurisprudence. And so that is an explanation for why the decision was made this way. And so if we ever want to use AI systems to make judicial decisions, which I don't think is a good idea at this point, they will have to produce explanations. But
so that's a great,
but more generally, I don't think explainability is a particularly useful concept. So first of all, most of the people, most of the things that people do, and certainly animals do, have no explanations whatsoever. Your taxi driver, you may trust, or Uber driver whom you may trust to drive you safely to another place. not only you cannot explain how they drive, they cannot explain how they drive, because most of it is, in the deep corners of their brain that, for which we have zero explanation. If we had a good explanation for how the brain was capable of driving, we could write programs to get computers to drive our cars, and we can't. So most of human knowledge is, below linguistic level and not explainable at all.
Right. I guess you're making this distinction that, especially when it comes to sort of perception kinds of problems, it's like, I don't need to explain to you why that's a tree that I'm looking at. It's a tree. I'd recognize it. But if I'm, denying someone bail, then I'd better have like really good reason and an explanation for that. So it's almost like you have two classes of systems, where, in one set, explanation is irrelevant. It does a good job of, doing what it's supposed to do, and you accept that. And others where it really matters, and those tend to be sort of, areas, where there's sort of human decision making and justification required for decisions.
That's right.
Yeah. So, one last couple of things, and, just curious about your thoughts about consciousness. Is that something that's totally in Twilight Zone and we don't need to think about it? Or is this something that is, possible in the next, I don't know, call it 50 years? Do you think we'd have machines that actually exhibit some kind of consciousness?
Okay, there's several ways to kind of formulate this. One first question is, will it be possible eventually to build machines that have the same level of intelligence as humans in all the domains in which humans are intelligent? And my answer to this is absolutely yes. There's no question this will happen. So there's going to be a point, it's not clear when, it could take a long time, where machines are going to be as intelligent as humans in all the things that humans can do. So that's the first thing. The second thing is, what is consciousness? And nobody really has a very good definition for what consciousness is. So until we have a good definition, it's very difficult to answer the question, will machines have consciousness? So I have kind of a folk theory of consciousness, which I'm told by our dear colleagues in the philosophy department who are specialists of that question, is actually, not completely unheard of or stupid. And it's the fact that consciousness is actually a reflection of the limitations of the human brain, not of its power. And I can explain this a little bit. So the front part of our brain in humans, it's called the prefrontal cortex. One of its main functions is this ability I was talking about earlier of being able to predict what's going to happen in the world, right? So predict in advance, not necessarily predict in time, but, if you watch, if I watch you right now, I can see your face. And even if I've never seen the back of your head, I can have some good guess about what it looks like. And it's because, I know a lot about how humans are supposed to look like, right? So, prediction of things you do not currently perceive, an essential ability of intelligence. I like to say the essence of intelligence is the ability to predict. And that's basically the front half of your brain doing this. It does other things, but it does that. Now, here is the thing. When we face a situation and we have to solve a problem to get out of that situation, we focus the front part of our brain, or prefrontal cortex, to the situation at hand. We configure the frontal part of our brain to basically modeling that part of the world that we are interested in. And we need a system that basically watches over that engine, that simulation engine in our brain, if you want, and configures it for the situation at hand. And here is the problem. We only have one of those engines that can simulate the world. We can configure it to various situations, but we only have one engine. And so our consciousness, if you want, needs to figure out what is the situation at hand and then configure our frontal cortex to simulate the world, when we think about something or when we try to solve a problem. And so if we had lots and lots of those simulation engines in our head, we would not need consciousness because we wouldn't need to configure them. We would have so many of them that we could all, use all of them in parallel. But because we only have one, we need to have, some decision maker that configures it, and that may be what we call consciousness. Okay, this is kind of a crazy theory, which may be completely wrong, but this is kind of funny because it would show that the most mysterious aspect of the human mind, which is, consciousness that, only humans and some higher animals have, is actually, a reflection of the limitation of our brain.
Fascinating. That's amazing. I never really looked at consciousness as a as a limitation of our brain. I sort of always viewed it as this highly evolved capacity that humans have. Although, I don't know, like, dogs have consciousness too, don't they?
Well, I mean, again, it depends on how you define it. Dogs have some level of self-awareness and consciousness. Elephants do too, and dolphins and a lot of primates. So we don't know how to define it. We really don't.
Yeah. So Yann, before we wrap up, I guess I usually ask people sort of what advice they have for young people these days. You're a sort of role model in the area of AI and data science. What's your advice to young data scientists and AI getting into the field right now?
I'll start earlier, perhaps, like, high school students, right? It turns out there are a lot of high school students now who are fascinated by AI, and they start playing with, PyTorch and they download the natural language understanding system and they build stuff with them. So it's become such a pervasive technology, and it's so easy to use now that, you can play with it in the science project in high school. So for a high school student, I would say, like, learn things that have a long shelf life. So you go to university, study things like physics or, electrical engineering or math or, the more theoretical aspects of computer science. You have to learn to program because that's a useful thing regardless of what you do, even if you don't do science. So, learn to program regardless of what you do, and then learn enough math that you can deal with the math in AI. And then if you want to really sort of open your mind, either study physics or engineering or something like that. So things where what you learn seems to be not completely connected with, what you're interested in, but it actually is. So for example, the theoretical methods that people use now to analyze deep learning systems pretty much all come from statistical physics, which is kind of the modern form of thermodynamics. That sounds kind of odd, but it's the same math. It's the same mathematics. Statistics also has kind of some of that. So, you're better off studying this than studying, how you write an app for iPhone or Android, because that is likely to disappear in 5 years or 10 years or whatever.
Right.
So that's the first advice. Like, take all the math and physics course that you can.
Okay. Was there a second piece of advice?
I mean, this is
yeah. I tell people, computing is the new math. Learn
computing. There's no question. Learn to program. Learn computer science. I have a terrible confession to make, which is I'm not actually a computer scientist. I never actually studied my undergrad is in electrical engineering, and my PhD is in AI. But it's not like I took any course in. It's kind of the strange way, French PhDs work. So I couldn't claim to be a real, card-carrying computer scientist, strangely enough. But anyway, the advice for people who are interested in data science and things like this is, if you want to get yourself remarked or noticed, if you want, my advice would be to participate in an open source project, like make some contribution to either an open source project that already exists or, create your own, which is more difficult because it might not take off. But basically, people will look at what you know how to do by looking at your GitHub repo, essentially. So if you show that you made some real contributions, it means you understand the underlying techniques. It means you can program. It means you can get stuff to work. And, that will be kind of the thing that really sort of, demonstrates your capabilities without, doing all the way to doing a PhD or a master's. Now, if you are an undergrad now and you are interested in AI, you have several choices. Putting aside what I said earlier, take as many math and physics and course as you can and learn to program. There are programs now in data science, and those programs basically focus on techniques like machine learning, AI, computer vision, natural language understanding, etc., and various other things and statistics whose purpose is to derive knowledge from data and with the help of math and computers. And this is really a new discipline. You could think of this as a new discipline. At NYU is the Center for Data Science, which I helped create several years ago. And the Center for Data Science now has a PhD program, a master's program, and an undergraduate major in data science, as well as a minor. And so if you are really interested in AI and machine learning, you should probably study through a program like this, because it really focuses on the stuff that is both interesting and necessary for AI and machine learning.
Indeed. Great advice. In fact, I tell all our incoming PhD students how envious I am that they're entering the field at this stage of its evolution. It's a great time
Absolutely.
to be in AI. Yann, I really want to thank you for your time and sharing your perspectives with the rest of the world. Thanks so much again. I really
thank you so much
appreciate
for having me on. That was fun.